An infinitely charged plane field. The reason for studying the charged ring field, as the previous lecture was, is twofold. To continue practicing and setting up the electric field integrals, and two, we want to use that result to calculate the infinitely charged plate. The infinitely charged plate is one of the iconic electric fields of electrostatic. We've studied the point, the dipole, the infinite line, and now we need the infinite plane. To calculate the infinite plane field, we start with a two-dimensional charged circular disk, and let its radius get very large. Okay, so that's the point here. So now let's do the two-dimensional finite charged disk. So we're going to assume all of the usual stuff. Okay, so we assume uniform surface charge, charge density, that is. In other words, we set this guy equal to a constant. We're going to start with the radius of r and the observation point P is on the z-axis. So I'm really mimicking the charge ring field setup because we really want to use that to make the calculation much easier. So now, if I set up a picture, then I imagine that I have something like this. I'm going to set up a coordinate system where this is x, y, and this is z. And then I'm going to set up my disk. So here's my disk. Now note that I'm drawing a thickness here. But you got to remember that I did just want to draw a circle like this, but I wanted to give the appearance of a disk. So when I'm looking at this thing, what you're seeing here is that there's no thickness on this disk. So then here's my z-axis right here. And then I'm going to pick a point right here. And this is going to be my observation P. So what do I know about it? I have uniform charge density, right? It has uniform charge density. And immediately we could say that from symmetry is going to kill all components except Z, just like the disk. In other words, I expect that the electric field of the finite disk to be in the Z direction. So once again, symmetry kills off all components except the Z1. Again, we knew that right away. So now the question that we're asking here is, in our first step, what is the physics of the finite disk field? Right? What is it? Well, there's two places, really. There's really two critical points that we want to look at. So I would say that there are two critical points. The first one, as Z gets much, much larger than R, the disk appears as a point charge. So again, if I look at the situation, I really have this. So if I'm close to the disk, right, and I have charge on this guy right here, what I'm seeing here is that I'm going to have my z-axis right here. And if this is my point P, what I expect, you know what, I did not want that there. I'm just going to say I'm going to focus on the field. The field here, we already know, has to be the field of a disk. And in this situation, we're looking at distances that, let's say, are that big. Of course, it's arbitrary. Now, if I pick a charge, excuse me, not a charge, but if I take that disk and I move really far away, so in other words, this distance is a very large z value, and what I expect at point P here, I expect that the field at this point should be that of a point. So in other words, physically, we expect that as z gets much, much bigger than r, E of the disk should then be the same as E of a point. So that's something that we have to check. Now, let's look at our second critical point. As Z is much, much less than R, the finite disk now appears infinitely large. It appears as an infinite plane. It appears infinitely large since we cannot see the edges of the disk. And that's not too surprising because I'm assuming that if you're in a small boat in the middle of the ocean looks infinitely large. Now, we don't know exactly what that field looks like, but that's the whole reason for doing this. We want to calculate this thing right here. Okay, so now in this picture, what am I seeing here? I have a disk. And then here's my disk. And once again, if I look at a point somewhat close to the disk, what I'm seeing here is that I'm going to get a field that's going to give me that of a disk. And I'm going to say that this distance here is, again, let's say that this distance from here to here is that distance z that big. Now what happens here is that if I get really close, I don't realize that there's an edge. All I see is that when I get here to this point P right here, it's super, super close, right? In this case, we're talking about Z being much, much smaller than R. What I'm seeing here is that intuitively, it has to be a constant field because that field, if it's flat everywhere around me, it has to be the E field of an infinite plane must be a constant. So why would I say that? So if I look at a picture of this thing again, let's imagine. So if I have a plane like this, and this is my field right here, excuse me, my plane, if it's infinitely large, I'm like infinitesimal point right there. So remember, I'm right above the surface of it. I'm not at zero. But then I start looking at the field lines. So no matter where I walk, everything is going to look the same. And because it looks the same, it has to be that constant. So what we expect then in the limit as Z gets much, much smaller than R, the electric field of the finite disk should appear as an infinite plane, and we expect that thing to be a constant. Note that that was not true of the infinite wire. The infinite wire, or the infinite line charge, as Z got much, much smaller than R, is not a constant. So if you're looking at this, so for example, here is if we look from infinity to the back of a wire, what do I see here? Well, I see my wire, and it's like this. And then what I'm seeing here is that I have a positive charge. So what does that field look like? You're seeing that the field is not constant because it's constantly changing directions here. Now we want to define the charge element dq. Step 2. Define the charge element dq. So the charge is going to be distributed uniformly on the surface. So if we have a uniform charge distribution, we then write that eta is equal to a constant, which means that I can define it two ways. I can define it as the total charge over the surface area. And if I look at this thing, well, since the surface area of a sphere is pi r squared, or a circle, excuse me, is pi r squared, and if the total charge is q, then that immediately tells us what eta is. So I now know that in terms of charge on the radius, but that's not the important thing. We need the details of the dq dq A. So this tells me that now I can define my charge element using dq eta dA. As you're going to see, there's going to be some required care here to calculate what that area element is. So the trickiest part is determining how to calculate dA. So what we're going to find is that in order to write the details of this, we have to ask, how are we going to integrate over all of the dA area terms? So to write out dA, we first have to figure how to sum little dA areas or little dA terms to get the total area of the disk. So now here's what we want to look at. The whole reason for our thing that we did with the ring charge was specifically this, for this reason here. So physically, we can add up little rings, just like our previous example, to arrive at the area, to arrive at the area. So picture-wise, how do I start to imagine this? So I want to draw a big disk. So here's my disk. And I know that this is a circular disk here. Now I'm going to say that this is the center of the disk. And then what I'm going to start to do here is that I'm going to start adding up infinitesimal rings. So I'm going to take this ring, and then I'm going to add it to my next ring. And then I just keep adding them up, right? And as I add them up, if they're infinitesimally thin, then what we can see here is that I'm going to add up all of the infinitesimal rings. And that's how I'm going to get the area. So now what I'm going to focus on is a single thin ring. So as I look at my thin ring, I could imagine that I'm going to have a ring that's going to look something like this. And I want to make this ring thin. So then here's one of the rings that I have. So if I have this, now I imagine that I have to set up my axis. So let's say that this axis that I'm going to choose, let's say that this is the y direction and this is the x direction. So I'm going to integrate along the y direction, which then means here that this is going to be y. And what's y? Y is the inner radius. And then I'm going to say that dy is the thickness of the ring. So then that means as I go all the way out to the outer ring, that has to be y plus dy. So then y plus dy, that's going to be the outer radius. So now we can calculate the area of a single ring. To calculate the area dA of a single ring, we know that we have to get an area, so it's got to be what? It's got to be the width of the line of the inner radius, right? So it's going to be dA is then going to be the circumference of the ring. Now remember, that's infinitesimal. But then I'm going to make the line thick by multiplying this by the thickness of the line. And so when I write this out, I have the circumference, which is 2y, and then the thickness has to be dy. And that has to be how I'm going to look at the area. So now I can put everything together. So putting all of this together, we started with eta equal to dq dA. Then we said here is that dq is then going to be eta times dA. But then if I write out the details, it's now going to read 2 pi eta y dy. And there is my charge element right here. Now we move on to the next step, step 3. So now we want to calculate the displacement vector and field, my little dE of the disk. Oops, wrong. So now let's set this up. Now the setup for the disk is identical to the thin charged ring, because I'm integrating over rings. So I'm just going to summarize the results. So I will summarize the results. And if you need more details, go back to the charged ring video again and watch it. So here I go. So I have a ring. On this finite disk, and I'm going to pick this as my center point. So I am seeing that this is going to be my z-axis all the way up to point P. Okay, this is going to be point P. So now I have my thin ring, and I'm going to pick a tiny, tiny amount of charge right here, and that right there is going to be my dq. So now that dq applies a field. It applies a field at P. So then if I start to look at this guy, it gets to right here, and it's going to apply a field dE. And this dE here, this is the field of a single ring. Now, when I start to look at these angles here, you can see here that if I look at just the geometry, this will be my angle theta. That's going to be my displacement. This is going to be my side z here. And then this ring has a radius of y. So I have all of the geometry here. But we know already from symmetry that I only have a component that's going to be pointing along the z direction. So if this angle and that angle are the same, now you can see here is that let me say if I move that little dE right here, you can see that this little dE is the hypotenuse of the triangle. This little dE right here of the ring is the adjacent side. So this immediately tells me here that the field of the ring using the geometry has to be dE times cosine of theta. And then we have the details that we've already talked about. So what are the details? Well, we know that the magnitude of the displacement is r squared, will then equal y squared plus z squared. We know that the directional cosine of theta is going to be y squared z squared square root into z. And then finally, we defined already that dq was equal to 2 pi eta of y dy. So now we have our little field here. So putting this all together here, so this is the little disk field from the charge element dq is d of the disk, which will then be dE cosine of theta, which will then be 4 pi epsilon into 1. And then I'm going to get dq r squared cosine of theta. So then all I'm doing here is that I'm going to get all the displacement information right here. And so if I put this all together, I get a field that then reads like this. After some cleanup, I'm going to get 2 pi eta z 4 pi epsilon naught. Then I'm going to get an expression y squared z squared to the 3 halves divided into y dy. And this is the field that we've been looking for. This little field right here. So now the last step goes something like this. We need to integrate over all the little disk field. So to get the area of the disk, our limits are 0 to r, which gives E of the disk, and I'm going to go from 0 to r, a little dE disk like this. And remember that z is a constant. We're integrating over y. So then I could pull out the constant and then I'm going to go from 0 to r of y squared z squared to the 3/2 of y dy, and that's our integral. Now, what would I do? I'd probably look it up, but it's not a hard calculation, just like the other one that we looked at. It's not a hard calculation, but let me give you some hints. So, hints to integrate yourself. So I would use the substitution. Let's say u equals y squared z squared, which then tells you that du is then going to be 2y dy, and change the limits from, let's bring it down here, 0 to r to z squared to r squared plus z squared. Another way that you could do that, I just Googled the answer and found that after some cleanup, E of the disk was equal to 2 epsilon eta of 1 minus r squared z squared square root into z. This is our field equation.